Welcome to UPSC Study Academy, empowering aspirants and shaping futures.
Today, in our exploration of communication systems, we embark on a journey into the dynamic realm of multiple access methods. We'll uncover the intricacies of frequency division multiple access, FDMA, code division multiple access, CDMA, and time division multiple access, TDMA. These techniques serve as the backbone of modern telecommunications, enabling efficient sharing of resources and facilitating seamless communication. Join us as we unravel the fascinating principles behind each method and discover their crucial roles in shaping our interconnected world.
Let us start with FDMA. What is FDMA? FDMA stands for Frequency Division Multiple Access. It's a method used to allocate a unique frequency band to each communication channel. In other words, each user is assigned a specific frequency to communicate over, allowing multiple conversations to happen simultaneously without interference.
One of the common applications of FDMA is in older cell phone technologies, specifically in the first generation, 1G analog cell phone systems. These early systems relied on FDMA to manage multiple calls. In this setup, each call was allocated a distinct frequency band. When you made a call, the system assigned you an available frequency, ensuring that your conversation wouldn't mix with others.
How does FDMA work? Frequency division. FDMA works by dividing the available frequency spectrum into multiple non-overlapping frequency bands. Each frequency band is assigned to a specific user or communication channel. These frequency bands are typically narrow and spaced apart to minimize interference between adjacent bands. Channel assignment. In FDMA systems, each user or communication channel is assigned a unique frequency band for transmission. When a user initiates a call or data session, the system assigns an available frequency band to that user for the duration of the communication session. Modulation. Before transmission, the user's voice or data signal is modulated onto the assigned frequency band. Modulation involves varying the properties of the carrier signal, frequency, amplitude, or phase, to encode the user's information. Different modulation techniques can be used based on the system's requirements and the characteristics of the transmission medium. Transmission. Once modulated onto the assigned frequency band, the user signal is transmitted over the communication medium, such as a radio link or a coaxial cable. The transmission may involve amplification and other signal processing techniques to ensure that the signal reaches its intended destination with sufficient strength and quality. Reception. At the receiving end, the transmitted signal is received by the corresponding receiver equipment. The receiver is tuned to the frequency band assigned to the transmitting user, allowing it to capture the signal while ignoring signals on other frequency bands. The received signal is then demodulated to recover the original voice or data information. Interference management. Since multiple users are transmitting simultaneously on different frequency bands, it's crucial to minimize interference between them. Techniques such as frequency planning, which involves allocating frequency bands in a way that minimizes interference, and guard bands, which separate adjacent frequency bands to prevent overlap, are employed to manage interference in FDMA systems. Call termination. Once the communication session is complete, the assigned frequency band is released and becomes available for reassignment to other users. This allows the system to efficiently utilize the available frequency spectrum by dynamically allocating frequency bands to users as needed.
It's important to note that FDMA is typically used in analog communication systems rather than digital ones. In analog systems, signals are transmitted in their original form without being converted into digital data. This makes FDMA an effective way to manage multiple analog signals simultaneously.
Despite being less common in modern digital systems, FDMA is still used in various applications today. It's employed in satellite communication, where different frequency bands are allocated to different users to prevent signal overlap. FDMA is also used in some radio and television broadcasting systems to separate different channels. Moving to TDMA. TDMA stands for Time Division Multiple Access. It's a method used to allow multiple users to share the same frequency channel by dividing the signal into different time slots. Each user is assigned a unique time slot within each frame, allowing them to transmit in turn. This means that several users can share the same channel without interference. TDMA divides the available time into slots, each user occupying one or more slots, while FDMA assigns separate frequency bands to each user for communication.
One of the most common applications of TDMA is in the Global System for Mobile Communications, or GSM. GSM is a standard developed to describe the protocols for second-generation 2G digital cellular networks. TDMA is a core technology in GSM, enabling multiple users to share the same frequency channel efficiently.
So, how does TDMA work? Time division. The available time on a communication channel is divided into multiple discrete time slots within a repeating time frame. Each frame consists of several time slots, and this frame structure repeats continuously. Channel assignment. Each user is assigned one or more time slots within each frame. This assignment can be dynamic, changing with each frame, or static, remaining fixed for the duration of the communication session. Synchronization. All users and the network infrastructure must be synchronized to ensure that transmissions occur in the correct time slots. This synchronization is often achieved using a central timing reference or control signals broadcast by the network. Data transmission. During their assigned time slots, users transmit their data in short bursts. Each user's data burst fits within their allocated time slot, ensuring that multiple users can share the same frequency channel without overlapping transmissions. Guard times. To prevent overlap and interference between adjacent time slots, small guard times are inserted between them. Guard times account for slight variations in timing and ensure that transmissions from different users do not interfere. Multiplexing and demultiplexing. On the transmitting side, the system multiplexes the data from different users into the appropriate time slots. On the receiving side, the system demultiplexes the received signal based on the timing of the time slots, extracting each user's data. Efficiency. TDMA efficiently utilizes the available bandwidth by allowing multiple users to share the same frequency channel. By allocating time slots dynamically, TDMA can accommodate varying data rate requirements and changing network conditions. GSM and TDMA. In a GSM, Global System for Mobile Communications Network, the utilization of Time Division Multiple Access, TDMA, is fundamental to its operation. GSM is a widely adopted standard for digital cellular networks, initially developed to replace older analog systems. It's renowned for its efficiency, robustness, and global interoperability. TDMA is one of the core technologies employed within GSM networks. It divides the available frequency spectrum into time slots, with each slot accommodating a single user's transmission. In the context of GSM, a single frequency channel is segmented into 8 time slots, facilitating communication for up to 8 users simultaneously over the same channel. GSM's utilization of TDMA offers several advantages. Firstly, it optimizes the use of bandwidth by allowing multiple users to share the same frequency channel efficiently. This maximizes the network's capacity and accommodates a larger number of users within a given spectrum. Additionally, TDMA in GSM ensures reliable and interference-free communication. By assigning specific time slots to individual users, GSM minimizes the likelihood of signal overlap or collision, enhancing the quality and clarity of voice calls and data transmission. Moreover, GSM's integration of TDMA enables efficient power management. During idle periods between transmissions, users' devices enter a standby mode, conserving battery life while awaiting their next turn to transmit or receive data. This contributes to extended battery longevity and improved user experience. Overall, GSM's adoption of TDMA as its multiple access scheme underscores its effectiveness in providing widespread, reliable, and resource-efficient mobile communication services. Through the seamless integration of TDMA within GSM networks, users worldwide benefit from enhanced connectivity and communication capabilities. Moving to CDMA. CDMA stands for Code Division Multiple Access. It's a type of multiplexing that allows multiple signals to occupy the same transmission channel by assigning unique codes to each signal. This optimizes the use of available bandwidth, allowing more users to communicate simultaneously without interference. How does CDMA work? Unique code assignment. Each user is assigned a unique spreading code, which is a pseudo-random sequence of binary digits. These codes are carefully designed to have desirable properties such as low cross-correlation with other codes. Signal spreading. Before transmission, the user's data signal is multiplied, spread, by their assigned spreading code. This process spreads the signal's bandwidth, making it appear as noise-like spread spectrum signal. Simultaneous transmission. Unlike TDMA and FDMA, where users communicate in distinct time slots or frequency bands, CDMA users can transmit simultaneously over the same frequency band. Each user's spread signal overlaps with others in the same frequency band. Orthogonal properties. Despite overlapping in frequency, CDMA signals can be distinguished from each other due to the orthogonal properties of the spreading codes. The receiver uses correlation techniques to recover the desired user's signal while rejecting interference from other user signals. Decoding and demodulation. At the receiving end, the receiver correlates the received signal with the corresponding spreading code of the desired user. This process amplifies the desired signal while attenuating signals from other users, allowing for reliable demodulation of the user's data. Interference rejection. CDMA systems can handle interference from other users, as long as their spreading codes are sufficiently orthogonal. This inherent resistance to interference makes CDMA suitable for environments with high levels of interference, such as urban areas or indoor environments. Dynamic resource allocation. CDMA systems can dynamically allocate resources based on user demand and channel conditions, maximizing spectrum utilization and accommodating varying data rates and traffic loads.
One of the primary advantages of CDMA is its resistance to interference and eavesdropping. The unique spreading codes make it difficult for unintended receivers to decode the signal, enhancing security. Additionally, the spread spectrum technique helps mitigate the effects of signal fading and interference, improving the overall quality and reliability of communication.
CDMA technology is widely used in various applications, most notably in mobile communication systems. It forms the basis of several cellular network standards, including the second generation, 2G IS-95, and the third generation, 3G CDMA 2000 standards. CDMA is also used in satellite communication and global positioning systems, GPS, where efficient use of bandwidth and resistance to interference are crucial.
Here's a comparison table outlining the key differences between FDMA, CDMA, and TDMA.
Don't forget to like, share, subscribe, and hit the notification bell so you won't miss the next part of our series on communication systems. Thanks for watching.